September 1st, 1859. English astronomer Richard Carrington was observing the Sun when he witnessed two intense flashes of light erupt from its surface, what we now identify as a solar flare. Unbeknownst to him, these flashes marked the beginning of the most powerful solar storm in recorded history, the Carrington event. Within just 17.6 hours, the associated coronal mass ejection, CME, slammed into Earth's magnetic field, faster than almost any other CME ever observed. The results were immediate and astonishing. Night skies lit up in blood red, green, and violet auroras, visible as far south as Cuba, Mexico, and even Colombia. People in the northeastern United States awoke thinking it was dawn, only to realize it was still the middle of the night. The skies were so bright that newspapers could be read outdoors without a candle. But what truly stunned the world was what happened next. At Infinity Beyond, we revisit this moment as the first time human technology met the fury of the sun. Across the globe, telegraph systems, the lifeline of 19th century communication, began to fail spectacularly. Sparks burst from telegraph machines. Operators were shocked. In some places, the lines caught fire. Despite being disconnected from any power source, the equipment continued transmitting signals, powered solely by induced geomagnetic currents created by the storm. Entire communication networks collapsed, and in many areas, repair efforts took weeks. The intensity of the currents overwhelmed copper wires, melted relay switches, and set telegraph offices ablaze. It was, quite literally, a fire from the sky. And all of this happened in a time before satellites, computers, or electrical grids. At Infinity Beyond, we ask the question, what if the Carrington event happened today? Unlike the 19th century, our society is no longer analog. We are digital, global, and interdependent. Nearly every aspect of modern life, from banking to hospitals to logistics, is run through vulnerable electronic systems. Imagine geomagnetic currents coursing through underground cables, overloading transformers, and melting power substations. Imagine satellites being knocked out of orbit or fed corrupted GPS signals, affecting air traffic and maritime navigation. Mobile towers fail. Emergency broadcasts vanish. Water systems, powered by electric pumps, stop working. Refrigeration fails in grocery stores. Hospitals lose backup power. And like the telegraph operators of 1859, we wouldn't even see it coming until the lights go out. Some scientists estimate that a modern-day Carrington-level event could cost the global economy over $2.6 trillion in the first year alone. Full recovery might take 5 to 10 years, especially for power grid infrastructures with long lead times on replacement transformers. Fortunately, awareness is growing. In the U.S., agencies like NOAA, NASA, and the USGS have established real-time monitoring systems. But early detection remains a challenge, especially for solar flares, which travel at the speed of light, reaching Earth in mere minutes. In our next segment, we'll explore how space agencies and governments are racing to build early warning systems, develop AI prediction models, and install protective infrastructure before the next big one strikes. Because if the Carrington event was our first warning, it might also be our last chance to listen. In the wake of near misses like the 2012 solar storm, and remembering catastrophic events like the Carrington event, governments and scientists around the globe have launched an urgent race, not to stop the sun, but to predict its temperamental eruptions before they reach us. At Infinity Beyond, we explore how space weather forecasting is becoming one of the most important and underappreciated scientific fields of our time. In the United States, the National Oceanic and Atmospheric Administration, NOAA, operates the Space Weather Prediction Center, SWPC, in Boulder, Colorado. This facility monitors solar activity 24/7 using ground-based magnetometers and a fleet of dedicated satellites, including SOHO, GOES, and the Solar Dynamics Observatory. When a solar flare or CME is detected, SWPC issues alerts to power companies, airlines, satellite operators, and even emergency services. Meanwhile, the U.S. Geological Survey, USGS, tracks geomagnetic field changes from 14 ground observatories. Together, these data points allow scientists to gauge not just whether a solar storm is coming, but also how strong it might be and which regions of Earth are likely to be affected. In the United Kingdom, solar storms are now included in the National Risk Register of Civil Emergencies. The UK's Met Office has established its own Space Weather Operations Centre, and the National Grid has begun installing new transformer designs that are more resilient to geomagnetically induced currents. During a major CME, the strategy would be to activate all 8,000 kilometers of UK power lines to evenly distribute incoming currents, reducing pressure on any one point in the system. But even with all these systems in place, there's still a problem: time. Solar flares, especially those classified as X-class, travel at the speed of light. By the time we see them, it's often too late to protect vulnerable systems. That's why AI is now being recruited to predict solar activity before it happens. Enter Dagger, the deep learning geomagnetic perturbation model, developed by NASA and university researchers. Dagger uses real-time data from spacecraft observing the solar wind and applies a deep learning algorithm, a type of artificial intelligence that learns patterns from past events to forecast future disturbances. What makes Dagger revolutionary is its speed and accuracy. It can issue predictions every 60 seconds and warn of geomagnetic impacts up to 30 minutes in advance globally. In tests using historical solar storms from August 2011 and March 2015, Dagger was able to precisely map the timing and geographic impact of the disturbances. At Infinity Beyond, we believe this is a game changer. Imagine a future where power stations receive automated alerts and shut down vulnerable sections of the grid just minutes before a CME arrives. Where satellite fleets shift into safe mode with seconds to spare. Where airlines reroute flights and astronauts retreat to shielded modules in orbit, all because a solar siren warned them in time. That future is beginning now. In our next segment, we'll follow the journey of the Parker Solar Probe, NASA's fastest spacecraft ever built, as it dives into the outer layers of the Sun itself, seeking answers at the source of the storm. Because to protect Earth, we must first understand our star. The Parker Solar Probe is humanity's most daring attempt yet to understand our star, not from afar, but by flying directly into its atmosphere. Launched in 2018, this NASA mission was designed to dive closer to the Sun than any spacecraft in history, traveling through the outer layer of the solar atmosphere known as the corona. At Infinity Beyond, we view this mission not just as a triumph of engineering, but as a desperate necessity in a world increasingly at risk from solar storms. Moving at speeds exceeding 690,000 kilometers per hour, or 430,000 miles per hour, the Parker probe is the fastest human-made object ever built. Its trajectory will bring it within 6.2 million kilometers of the Sun's surface, 7 times closer than any previous mission. To survive this extreme environment, it's equipped with a carbon composite heat shield capable of withstanding temperatures over 1,370 degrees, 2,500 degrees. But what's more impressive than its speed or endurance is its mission objective: to touch the Sun and bring back answers. By flying through the corona, Parker is collecting data on solar wind, magnetic fields, plasma flows, and energetic particles, the very ingredients of the storms that threaten Earth. The corona is where CMEs and solar flares originate, but until now, it has remained one of the most mysterious regions of our solar system. Why is the corona hotter than the Sun's surface? How does solar wind accelerate to such high velocities? And most importantly, can we predict eruptions before they begin? Parker's onboard instruments, like the Field Suite, SWEEP, Solar Wind Electrons, Alphas and Protons, and WHISPER, Wide Field Imager, are gathering unprecedented insight into these phenomena. Already, Parker has made groundbreaking discoveries, such as detecting switchbacks, kinks in the magnetic field lines that could explain how energy escapes the sun.